Okay, thank you very much for the invitation by the organizers. Beautiful campus. So, I will go straight to the main result. So sometimes people run out of time here. You know? I don't want to be one of them. So I will, the main theorem is simple to state, hard to understand, because I relate two seemingly very different geometrical problems. And so one of them on the right, I think it's easier to understand what it means. So you're rolling a ball along another ball, and there's a notion of monodrome, how much the rolling ball rotates if you go along a closed curve. So that's the one problem, the monodrome of a rolling ball. Can you hear? It's kind of disconnected. The other one is this, what I call dancing pairs. So it's a pairs of polygons, okay, red and black in this picture, in a projective plane. One is sort of inscribed in the other. The vertices of the red lie on the edges of the black, plus an extra condition. Okay, this was easy, inscribed, which I will describe. It's written some equation about with the cross ratios. And this I call dancing pairs. I'll try to explain what's the motivation, where it comes from. May not have time. So, but it stands by itself. It's an elementary notion of dancing pairs. And the main thing that these are two seemingly different problems in very different geometries. One is Euclidean or spherical geometry, what you call it. Another one is projective. They are the same problem, although it looks far from it. So that's the main, that's the subject of this talk. I'll try to explain this too. And the proof, here's the proof. I have to give more details, but basically the proof is that each one of these are, as usually happens in mathematics, are equivalent to a third object, which is much more fancy, like more abstract object, but it's a central object in mathematics, has been for more than 100 years, introduced by Cartan. So yeah, so I'll explain you what 1, 2, 3, 4. I mean 1, 2, 3, 4, 5. Yeah, how there's the equivalence of these two geometric problems to this this distribution, this Cartan distribution. Okay, so let's begin. Okay, most of these terms and concepts here, I think, for what I heard talks here, probably you're not aware, you're not familiar with. Yeah? No billiards, no integrable systems. So please don't hesitate. I already stated my main theorem, so you can stop me anytime, ask any questions you want. No problem. You don't have to wait to the end. Okay, so let's begin. Here is the same thing, but in a more fancy way. There's going to be like a preview of the main proof. There's going to be a 5-manifold. That's where this Cartan distribution lives on the top, and there's going to be two quotients, but just Z2 quotients, different Z2 quotients. One quotient is going to be this will be a mathematical model for this rolling problem, and another quotient will be a mathematical problem, model for this dancing pairs problem. Yes. Excuse me? No, I will now explain what's the mechanical problem exactly. No twist, no slip. That's the term, or no spin if you wish, instead of twist. Okay. The picture that shows spin? No. We will see in a moment. Okay, so that's going to be the structure. Okay, they're going to be two. They are not equivalent completely, but up to some mild you know, 2-to-1 cover, they become the same problem. Okay, so here is the, I begin with a more obscure one, the dancing pairs, where you're still quite awake. So, so what is a dancing pair of polygons? So the polygons are marked with them. The first one marked with by its vertices. I denoted by its vertices, A1 to AN. Second one by its edges for some reason. And then I first, there are two conditions. The first, as I said, one is inscribed in the other. Each red vertex is on a black edge. Okay, that's the easy one. And the second one is this equality of cross ratios. Cross ratios are several ways to define it. Here's the one we use. And what we're talking about. So you see, we extend at each vertex. We apply this condition, this dancing, this second equation, apply it at each of the n vertices, if you wish, of the black polygon, the first polygon. So what do? We extend, as this picture shows, we extend the edges, a black edge and the red edge gives you a new point. And then a red edge and a black edge give you 2 points. And then we form two cross ratios, the orange one and the blue one. And the equation asks for the sum, you know, the sum to be 0, one to be negative of the other. Okay, so that's the definition. Clear? Something is wrong with this definition for those who know about cross ratios. Nobody has a comment? Quiz for the audience. This picture cannot be true as is, because if you know about, you know, so it's this, and that. And then this, and that. They have the same sign. I'm not sure if it's positive or negative, but both the cross ratio have the same sign, so they cannot be, the sum cannot be 0. So as drawn here, it's good to remember, it's a good picture to remember the definition, but it's simply, they will not, this picture cannot obey this equation. Here's the correct one. It's more messy, but this one does satisfy the. Okay, so that's a dancing pair of polygons. I will look for closed polygons, pair of closed polygons. Although this, you know, just need for the second condition, you just need a sequence of 3 black dots and 3 red lines in order to check it at the point. It's quite easy, you know. For example, one way to think how you can construct such a dancing pair. You can begin with a polygon, let's say a black polygon, whatever you want, and then try to inscribe in it a red polygon which will satisfy this condition. So what would you do? So let's say I start, just go around, okay? You start with this, so you will take this as the vertex, as this vertex. So red lines, and for the third line, how do you put it? You'll use the equation here, so you get the third line. Well, it's not going to be like that, as I remarked. It's going to be something like that. The pictures are pretty horrible. I try to make nice pictures in a plane. They just go all over the place there. Okay, but so now you apply it here. You see, well, this intersect this somewhere. I don't know, here. So now you just equation here to produce the next red one. You go all around. There's no guarantee when you go back you can complete it. But then, okay, but remember I had these 2 red ones. I can play with this. Okay, it's not clear from this description that you can get any closed ones. All right. Although it looks reasonable, there are enough, you know, there are less equations and variables, so they should do it. But that's the definition. Okay, so it's clear the definition of dancing pairs. Excuse me. Yeah, it's not so easy, but it is possible. This is the picture I showed in the beginning. It was of pair of hexagons. Okay. And by this equivalence with rolling balls, it's actually very easy. That's kind of one of the points here. Okay, did I answer your question? All right, promise. Yes. Yeah, everything happens in RB2, RP2. Well, there might be or not. There's no, you know, you can have non-contractible things in RP2. Yeah, there's no restrictions on contractibility. It's a sequence of points, exactly. The sequence of points in the plane and sequence of points in the dual plane, like sequence of lines in a dual plane related. Okay, any more questions? I mean, this is the main definition of the lecture, so make sure you got it. Okay. Okay, there's some non-degeneracy conditions, otherwise this doesn't make really good sense. You shouldn't have 3 points on a collinear or 3 lines concurrent. And also an important one actually is, you know, the line in front of the point. I mean, it doesn't pass through the corresponding point. Okay. Other than that, it's arbitrary. Okay, this is the motivation. I don't think I'll have time. If you have time, I'll come back to it. Where does dancing come from? You know, people ask me. Well, there is a good reason, but I'm sorry. You want to go and penetrate into your next break with this fantastic food outside? I'm happy. Okay, here is the theorem that, well, it was not obvious to us at all, but there are no dancing polygons, there are no dancing pentagons, pairs of pentagons. The first case is 6, and here is the picture, and I will explain to you how by this correspondence with the rolling balls, it's very easy to get. Also, you know, if you I just see this picture, I didn't tell you the sizes, but there's only one parameter here. You know, what's the ratio between this size and this size, and you can just play with this ratio and solve this equation and show that there is a unique solution. Okay. This is my promised proof. Okay, let's move to the second item, rolling balls. So the rolling balls question is, here as Maxime asked, more specifically, we draw a polygon. I mean, each of the arcs of the lines of the sides of the polygon on the big sphere is an arc of a big circle, great circle, and we roll on it, no twisting as you go along, no sliding. Okay, when you reach a corner, you stop. You don't move the ball. Huh? You move then you start rolling there and running. The most intuitive sort of way of rolling around. And something very weird, I admit, I want the ratio of the balls, the radio of the ball to be 1 to 3. Okay, it sounds strange, but this whole magic works only for 1 to 3. In the dancing pairs, there was no parameter. Here there is a parameter, this ratio of radio of the ball. This magic works only for this ratio. Yeah, 1 to 3, 3 to 1. Yeah, I can roll the big on the small on the big. I just fix the small on the big. Easier to draw. Yeah. Excuse me? Yeah, you can do it on non-closed, but I will look for a closed path. Yeah, but I would look for, so I'm looking for, so what's the problem? No problem. So the problem is, so as you roll it along, you come back, they're going to be monodrome. The ball, typically, the rolling ball will not come back in the same orientation. We rotate it respect to its initial position. Actually, it's not, there's going to be a whole path in the orthogonal group, the group of rotations, which describe how it rotates with respect to its center of the rolling ball will rotate at each point. And so it will be a sequence of like a polygonal path in this in the orthogonal group. And this path may close or not. So this path is what I call the monodromy, the rolling monodromy. This path of the describing the rotation of the rolling ball. I didn't bring an animation, but I think this is it's easier to imagine. You don't need animation to that. So yeah, so I want this. So the condition is to find, the question here is to find a polygonal path on the big sphere such that the rolling monodromy is trivial. What do I mean by trivial? First, this path in the orthogonal group has to close up. Okay, I think it's on the next slide. Did I write it? Since then, the rolling one finds a path, rolling monodromy. Okay, here I just explained what is the monodromy. So here, for example, I will come back now to the question. So it's a bit counterintuitive if you go with this sphere, which is 3 times smaller than the big one. If you go around a whole great circle, it will rotate 4 times, 3 plus 1. Okay, it's a good puzzle. If you take 2 coins, for example, the one that rolls, it will rotate twice, not once. You can try yourself. Right, but in our case, it will be just part of the arc of a circle. So yeah, so in this, so I would say that it's trivial if this rolling monodromy, this path in the orthogonal group, is closed but not enough. It has to be contractible. Okay, the orthogonal group has some topology, some fundamental group C2, and if you go twice along the curve, it's always contractible. But if you go only once, it may not be contractible. Correct. To describe the configuration space of rolling is S2 cross SO3. I'm only looking at the SO3 part to define the monodromy. Correct. Yeah. Good point. Thank you. Yeah, I only look at the SO3 component of this path in this configuration space of rolling. And so here you see another kind of way, if you like it, you can, the 3 sphere is a universal cover, 2-to-1 cover of the SO3. So you can lift this curve, and if it closes up in universal cover, it's standard factor, then that means that it was the original curve and SO3 is contracted. Okay. Whichever. So remember my example of rolling around a complete great circle. So if now I take a triangle, this 90-90-90 triangle of a big sphere. So each one of its edges, it's a quarter great circle. So if the whole circle is 4 rotation, around 1/4 is 1 rotation. 1 rotation actually generates the fundamental group of the SO3, full rotation. So, or if you lift to SO3, it will end up not in the, you start in identity of S3, you will not end up in identity, it will end up in an antipodal point. And if you go along 3 of these arcs, you still end up in a, antipodal point. But if you go twice, then this closes up in SO3. That means that you get a trivial monodrome, going to my definition. And this picture of the hexagon, by this magic correspondence between the two problems, is exactly the one corresponding to it. You just do some plug into the formulas, and you get this nice picture. So, okay. So that's the problem of rolling balls with trivial monodromy. Okay, now the third ingredient that's supposed to connect these two things is this Cartan distribution. That's a big subject. I cannot explain it here if you haven't seen it before. I will say several words. So what is this object? This object appeared the first time I detected it is in Cartan's early Cartan thesis, 1892, something like that. And I don't know about this thesis. It's pretty interesting. His thesis was basically like elaboration of killing classification of simple algebras. There were gaps in this classification. He kind of classified the root systems. He invented this idea of attaching root system to simple algebra, and he classified the root systems, but he failed to show that each one of these possible root systems indeed is realized by the algebra. And so Cartan was informed by it. I was informed by a student of Sophus Lee about this gap, and he sat down to do it, and he completed it. And one of this, if you know this list, very famous list, so there are some kind of classical groups, classical algebra, and there's some 5 exceptional ones. And the lowest dimension exceptional one is called G2, it's 14-dimensional Lie group or Lie algebra. And Cartan, nowadays, if you open up Wikipedia, this is defined, I think, the automorphism group of the octonions. Okay? You know, complex numbers, quaternions, octonions. But that's not how Cartan defined it in his thesis. He defined it as the automorphism group of a certain rank 2 distribution on a 5-dimensional space. Which is the star of this talk. So, yeah. So later on, like 20 years later, he wrote a big article. This article here about the subject of rank 2 non-integrable distributions on 5-dimensional spaces. Everything was done locally, but so he proved this thing is like distillation of many results from him and many people afterwards, still under investigation. The one who is more expert about this subject is not here. Is Igor Zelensky. I don't know where he went, but I was hoping he would correct me. So, yeah, the main thing is that contrary to contact distribution, this is non-integrable distribution, as non-integrable as possible. 2, 3, 5 means that it's a rank 2 distribution. You take brackets, you get a 3 distribution, 3-dimensional rank 3 distribution. Take brackets again, you get 5. Yeah, that's the fastest that it can grow. There are some slower 1, 2, 3, 4, 5, 2, 3, 4 stops, all kind. But that's kind of the generic one. And contrary to main thing to you realize when you look at this subject is that it's more like Riemannian surfaces. Locally, they're not equivalent. I mean, take 2 random surfaces. There are some local invariants, curvature. Same thing here. If you take 2 such distributions, you don't have like Darboux theorem, like in contact and cyclic geometry. They are not even locally equivalent. And so one of the things Cartan studied is what is the maximum symmetry, kind of what is like the space forms in this world. And he found that this is a certain, it's a unique distribution which has this maximum symmetry, unlike in Riemannian geometry, we have like 3 spaces with maximum symmetry, but in here there's only 1. And that's what we call now Cartan distribution, this 2, 3, 5 distribution with maximum symmetry. The symmetry being this mysterious, I think still mysterious group G2. Okay, so And here I wrote for you just a formula. It's deceptively simple for this distribution, right? How do I write it? Just to write some formulas, not just abstract nonsense. So we look at R6. I think of it as R3 times its dual, as you'll see in a moment why. And then I look at a quadric, just the quadric of signature 3, 3, affine quadric, right? B times A equal to 1. And inside it, I write an equation. Right, I define a distribution, but the zeros of this equation between one forms. And it's pretty easy exercise to see this defines a rank 2 distribution. A bit less easy, but not so difficult to show that this is 2, 3, 5. If you take brackets, it goes up to 5 as fast as possible. Much more difficult is to show what is the symmetry group of this one. You need, I think, the full theory of Cartan to do that, but this is a fact. And yeah. Okay, another result. So, okay, you can use a general theorem of Cartan to show that this has a 14 dimension. We call it flat distribution, those which has maximum symmetry. Yeah, Cartan saw that the maximal symmetry that can happen is, in this case, 14-dimensional group of symmetry. The next case is a 7-dimensional symmetry. And there's a classification also of this, like maybe the analog of symmetric spaces in this word. Now, the way it is written, it obviously has 8-dimensional symmetry. Why? Just the group of SL3R. Yes, the linear group acts here. Why? Because I'm using this vector product, but this vector product, okay, it's kind of not the one that you usually use Euclidean structure, but no, it's a vector product that takes value in the dual space. Okay, you take two vectors in R3 and you plug them into the volume form, and you get a one form. So it takes value, so it's invariant under the linear group that preserves this volume form. So that's why it is the way it is defined. It has SL3R obvious symmetry, but SL3R is 8-dimensional, and Cartan proved that the submaximal symmetry is 7. So necessarily it has 14-dimensional symmetry. Absolutely non-obvious, but this is the case. Okay, that's all I would say about the Cartan distribution for the moment. And question, yes? Yeah, this is a kind of a vector equations. For each of the components, it's this 3-1 form, and you can see it is it is transverse to the I did it. Okay, any more questions? Yeah, I welcome you to take these equations and try to play to show. Takes a while, but it works. Yeah, the equations that Cartan gave are similar, but I think this is simpler. The gaps in the thesis are similar, but these are somehow nicer. Well, not for me to say. Okay. So we have, where is how much time I have? It's okay. Okay, so now the arrows. What is the relation between each of these two problems that I posed in the beginning to this Cartan distribution? So it's a geometrical model. So the first one is the one that David pointed out. So I call it Q roll. The configuration space of rolling is just, you're given by a point and on the big sphere, touching the contact point of the two spheres and the amount of rotation of the small sphere. And this condition, if we do some kinematic calculation, like this condition of rolling without slipping and and twisting can be written quite compactly in a set of linear equations on the tangent bundle of this configuration space. So it gives you, it's pretty easy exercise to check, it gives you a rank 2 distribution. In fact, a 2-3-5 distribution for any pairs of surfaces, in fact, balls or whatever, plane and a ball or whatever. Okay. Now, you can also check, it's also pretty easy to check that it always gives you a 2-3-5, it's almost always give you a 2-3-5 distribution, like the maximally non-integrable. So then the question is, when is this, what is the condition, geometric condition on this pair of surfaces? You're rolling one along the other without slipping and twisting, such that the associated 2-3-5 distribution is flat, is Cartan distribution. Okay. This question, as far as I know, is still open. Well, Robert Bryant, who is the world expert on such things, worked hard on it, and I informed firsthand doesn't know how to solve it. But there are partial answers. If you're rolling, let's say, a sphere on a sphere, then the answer is that it is flat, as you may guess, when the ratio of the radii is 1:3 or 3:1. Okay. Also, you can roll, negatively curved surfaces, more difficult to draw, but then it's also the same thing. When the ratio of the curvature, if you want, is 1:9 of rolling. Okay. There are cases when it is 2-3-5. I mean, it is a flat, it is Cartan distribution, which is not of what I said. Okay, you can, there are examples of surfaces of revolution rolling on a plane. That's the first thing you will try, but they have to be very special shape in order to be flat 2-3-5 distribution. Okay, but this is still a mystery. If someone wants an open problem with strong calculational, characteristics, that's a good one. Okay, so that's that's Robert Bryant. He just told me this 1-2-3 miracle in a conference like this more than 20 years ago. He never wrote it up, as far as I know, but other people, including me, wrote it up and informed about this. He said this is just Cartan. It's not worth writing. Just everything is in Cartan. That's like his favorite. Okay, inside this 2-3-5 distribution, I didn't mention it, but there's something called rigid curves. There are remarkable curves, there are horizontal curves, like integral curves of the distribution, which have this rigidity property, which kind of all calculus variation breaks down. You cannot deform them. They're like isolated points. When it fixed two endpoints, you cannot deform them. You see, if you put any metric, I didn't put any metric, but if you put any metric, like sub-Riemannian metric, there will be automatic geodesic. Okay, because there's no way to deform them. So this is a pretty amazing property. Bryant and Lucas Shu, his student, wrote a beautiful article about this subject. And for a rolling case, it is very easy to describe these rigid curves, because these are exactly the ones I'm going to use in my relation with the two problems. They are just, when we take the rolling case, it's just rolling along geodesics. Yeah, when you roll along a geodesic, a great circle of one of the surfaces, it's going to be also a geodesic in the other surface. They lift up to this rigid curves. I will not say much about it, except that this is, well, I wrote with Richard Montgomery also an article about this subject, trying to clarify this mystery of 1-2-3. I don't know if we succeeded. Okay, so that was the rolling. Now I have to tell you quickly about how is dancing modeled by the same distribution. Okay, so the way it is modeled, I already prepared the ground by giving you this model for this Cartan distribution. Well, we just think of B as homogeneous coordinates of a line in RP2, and A is homogeneous coordinates of a point. Okay, So so you see this sort of this 5-dimensional quadric, it's sort of fibers over the product of a plane, projective plane, and it's dual. And with this some 1-dimensional fiber, whose role I will not explain now. Yeah. So it turns out, and this is probably the main thing which I'll spend least time on, when you have this dancing polygon, right? It's closed or not, dancing polygon, it lifts uniquely. Yeah, there are many ways to lift it, but there's a unique way to lift it to a horizontal sort of polygonal curve or piecewise rigid curve on this. Yeah, that's the main technical lemma that makes all this work, but I don't have now time to explain it. It's will come up in I don't know, hopefully in 1 month in a paper. You can see it all. Yeah, so that's the magic of this transformation, is that dancing polygons are just like projection onto the projective plane. These cross ratio equations of something which is very simple from an abstract point of view are just like when you take a curve on this 5-dimensional quadric. In this case, this rigid curve are just actual lines in R6. Yeah, they're just actual lines. Exactly, lines are contained in this quadric. And when you have and the lines which are horizontal everywhere, exactly to this, by considering the vertices of this polygon on this quadric, you consider them as homogeneous coordinates of pairs, point and line, you obtain. Of course, we came from that, and then we projected, and we try to say it in a purely projective geometric terms. Yes. Yes, but remember, one of my third non-degeneracy condition was that it does not lie. That the point. No. It's a good question. Okay, I mean, it's pretty dense. I said that, you know, this point does not lie on this line. It's one of them. So that's exactly, it means that it's homogeneous coordinates of this point. Homogeneous, let's put like a 3-vector, right? And homogeneous coordinates of this one are not 0. But then you can choose the coordinates, so it will be 1. So there's always, when you have a pair of non-incident pair of line and point, you can always lift them so they satisfy, so they lie on this condition. There are many ways to do it. There's a 1-parameter way of doing it, but when it is dancing, there's a unique way to lift it, to connect it up. Yes. Correct, but it's very difficult. But okay, our proof that there are no dancing pairs of pentagons, for example, we are working there. We show that there's no horizontal closed horizontal polygon on this Q. That's much easier. It becomes a quite elementary exercise when you work up there. When you work, we try to mess up with the cross ratio. You can do it also, but it's a big mess. So, well, okay. This is almost the end, so feel free to ask more questions. Yeah. Okay, this article is an article I wrote several years ago with my co-author in this work, and Pavel Nurovsky, who big expert on this, everything Cartan, who introduced me to this subject. And that explains the motivation. I mean, this work is like a discrete version of the continuous version, which is explained in this other article. We were led to this. Yeah, there are dancing pairs of curves also in the projective plane. Okay. Yeah, yes. Yeah, there's G2. Here, this is explained here. Sort of. Well, imaginary split octonions. That's the G2. Yeah, well, so this kind of pretty strange. How can be G2 come into this business? Never G2, as far as I know, been seen in any problem in projective geometry. Well, here it is. So this is an affine quadric. It has a natural, compactification inside as a compact. Where it is here. Topologically, is this what is written here? And this quadric is a quadric also of this signature in RP6. And RP6 you should think of as projectivized imaginary octonions. But also you have to take the two versions basically of octonions. The usual ones whose symmetry group is compact G2, and there is split octonions, so-called, whose symmetry group is our G2 here, is non-compact group. And yeah, so that's the yeah, all this we were established before, and once you compactify, so this you remember in my double fibration diagram, that's how you fit all this dancing pair business into this big diagram. You have more questions? No? Okay. I think the next one is, yeah. So you see this configuration space of dancing pairs is the open dense subset of this projective quadric. And this projective quadric is naturally acted on by the G2. The distribution also can be defined also in the language of octonions, so it's automatically invariant under G2. And then, so in principle, we know by Cartan that these two distributions are locally equivalent, but we found a global, this diagram shows you how they are globally related by the both of them are the Z2 quotients of the same object. So to summarize, this is summary. So if you roll something there, if it has a if the see the condition I gave that the rolling monodrome also closes up when you lift it up to S3 is the condition that tells you that up there the curve is closed. The rolling curve is closed when you lift it to S2 times S3, and then you can project it, you get a closed curve in this dancing configuration space. Everything is a distribution behind everyone, and all these maps preserve the distributions. So that's the question of how do you come up with the polygons in this. So once you believe all this correspondence, you have to solve one of the problems, one or the other. If you make two problems isomorphic, then you didn't solve anything yet. So it's much easier, we found, to find the closed polygons on the sphere with trivial monodrome. So we just generalized this example of the triangle. We just look for equilateral, like irregular polygons on the sphere, checking carefully that they have trivial monodrome. That's pretty easy. You think first you have to do kind of complicated equations on the orthogonal group, to take product of matrices that gives one. Sounds pretty horrible, but actually this has a geometric interpretation. You just have to check that the the other regular polygon you get on a small sphere also closes up. And there is a mild this condition about contractibility can be solved. So, well, this lemma summarizes it all. And here I give examples, another hexagon. And this is the number of vertices. And there's this kind of rotation number around some center of this polygon. Okay, this is a pretty elementary spherical geometric problem to find polygons. And I think I'm done. Here is the first slide. Put again if you want to ask questions. Do I have another one? No, that's it. Oh. It's the same. Correct. Yeah. Yeah. Exactly. So that's, yeah, that was, remember there was a slide I skipped in the beginning? Well, that's the explanation to that. They are the same question, basically. The dancing comes from the continuous version of this, and which is your second question. No? So, yeah. Okay, first I put the slide so you can enjoy the movie. Even if you cannot follow what I'm saying, it's always a good idea to give you exactly. So what is the continuous? What is the continuous version of? What I mean, we have two curves, one inscribed in the other. So that's what we see. That's the dancing condition. So what we imagine is a line. This line is the ice skate of a beautiful ice skate. I think it's the most beautiful of Olympic sports. There's no question about it. I think it's so elegant and graceful. So imagine a skater. Okay, that's the red line. So the red line is moving, right? You're always skating, and at each point, so it's all so it leaves this mark on the ice, right? So the line is always this red line. Let me see. This red line is moving. Imagine it's the ice skater, and it's always tangent to this envelope of these lines. Okay. So there's at each point there's imaginary, like I would call it the turning point of the line. Every line, how does the line moves in a plane? Always one way is just to turn around the point. The statement is that unless it moves, parallel to itself, it's always turning around some point, the turning point of this motion, instantaneous turning point. Okay, and then there is this guy. He is not skating. He's just running around the ice, trying to chase this skater. How would he do? Well, he always has to. That's the rule of this dancing rule, this choreography rule. He always moves in the direction of this turning point. That's where she's most likely to be. That's usually the turning point is below her foot. So yeah. So the question is, in the space of pairs, point, line. These are just this condition. It's a kind of, again, a non-holonomic condition that the point always moves in the direction of the turning point of the line. This condition turns out to be the condition of being tangent to some distribution of quadratic cones on this four manifold of non-incident pairs, point, line. And this is one of the most beautiful objects I've seen. It's like it's a metric. It's a pseudo-Riemannian metric of signature 2,2. It's the analog of the Fubini-Study metric. For many points of view, many of the formulas coincide, but it's defined purely in terms of incidence relations without any, Fubini-Study metric. It's nice, but it's pretty arbitrary. This is like God-given, if you believe. So Yeah. So you see, this condition, this is the analog of being inscribed, you see, because what is this turning point? Is the intersection of two nearby infinitesimally closed lines. So these are sort of the vertices of the red poly. Yeah, and what is this tangent line? This is the line passing through two nearby points. Okay, so this condition that this red point there is lying on this tangent line is exactly the continuous version of this being inscribed. And now the second condition. So this is pretty easy. The second condition of this mess with cross ratios. Well, here is written a sentence in the language of pseudo-Riemannian geometry, but I will not go into it now. If you want, this is the whole article that I showed you. The one from 2018 is dedicated to this. It's something called half geodesics. You have to know a little bit about pseudo-Riemannian geometry in signature 2-2. It's a very natural condition, but we were trying to give it in purely projective geometric language, and we basically failed to do it in this continuous version. But in a discrete case, it is possible, and that's what the first slide I gave. So I don't know. Does this look dancing enough to you? This picture? Self-dual. Yeah, I have to explain. This is in this signature. If you have a null line, it's always intersection of two null planes, one self-dual, one anti-self-dual. And the condition on the curve is that the self-dual tangent plane is transported in a parallel fashion along it. So it's like, we call it half geodesic. So it's, yes. In this case, a big mess. It's a big mess. So we struggled with it for a long time. And then said, okay, let's give a chance for a discrete version. And discrete version, I wrote you, okay, not a very simple formula, but pretty elementary that everyone can understand if he wants to. I heard only 1/3 of your words. What? Yeah, it is very symmetric. You can, yeah. No, because I show the picture in the projective plane, but you can draw exactly the same picture in a dual projective plane, and there it will be exactly the same picture, but red and black will be transported because of, instead of a red line, you'll have a red point in the dual projective plane, and then you check that this condition, yeah, it looks exactly the same in the dual projective plane. You know, you can draw a line as a line in projective plane or a point in dual one. You can draw a point in the projective plane as a line in the dual one. So if you transform it to the dual picture, it looks exactly the same. The condition is exactly the same. So I think that's what you meant by symmetric, no? Okay, so the answer is yes. It's symmetric. You like the double vibration? Yes. Oops. Let's read the double cover of the orthogonal group, the three sphere. So I mean, forgetting about everything, this diagram, take 2 sphere times 3 sphere. And on the right, here I forgot in the first. Okay, good question. This is it just so happens that that this quadric, that this projective quadric, closes up Yeah, if you can just construct a diffeomorphism between this projective quadric. You look at six-dimensional projective space. You use 7 coordinates, and you write the equation for a quadric. You know. Okay, so the quadric that parameterize this dancing pairs, this one is sitting, this I call it Q dance, is sitting in R6. Okay. This R6, you should think of it as an affine chart in RP6. Yeah, okay. Here. The dancing space is a 5-dimensional quadric, affine quadric, in 6-dimensional space. The product of R3 and its dual. Excuse me. Which picture? There's no picture here. What? The B is a 3-dimensional vector. It's I think of homogeneous coordinates of the line. And the A is also homogeneous coordinates of the point. So